All right. Good morning, class. Um, so anyway, I guess so for today, we're just going to continue with some more graph theory sort of traversals, or actually one graph theory traversal. So we went over so far depth first search with graphs, and we went over sort of two different types of applications of depth first search. One was to detect a cycle in the graph, and one was to have a topological sort of a directed acyclic graph, which I guess they have their uses in different applications of graph theory, but just, went over those examples. So now we're going to go over a different graph theory traversal, which will be known as a breadth first search. So I guess without any further ado, without any more delay, I'll go ahead and begin a screen share, and then we can go ahead and just get right to it. So just so I don't have to rush, I'll have enough time to cover this example. If I finish a little early, that's okay. I can always cover newer stuff. Since we don't have too much more time left, we only have a few more lectures left because next week is our last sort of week of actual new material. Because after Thanksgiving week, we have our study week, so definitely getting towards the end. So breadth first search. Okay, so yeah, I guess time flew by. It felt like an eternity early in the semester, but I guess now it feels like time flew by. I mean, this class was fun, but a lot of stuff happened, like a lot of new things at once, which was really kind of hectic at times. It was still a fun semester, but very busy nonetheless. So I guess once again, it's a graph traversal. It's not really a search, although you could use it to search a graph, I suppose, but really it's a traversal type. And I guess, depth first and breadth first are the key words. So depth first means you want to go as deep as possible in your graph. Breadth first, you kind of go, I don't know how breadth works out here, but it's a level order traversal of your graph. It's a level order traversal. So what happens is, basically, if you are processing a node B, all of B's neighbors are processed before B's neighbors' neighbors. I don't know if it's actually the correct grammar. So basically, you're at node V. You first process all of its neighbors before the next level of neighbors get processed. If that makes any sense. That's sort of the idea with breadth first search. So a breadth first search is actually going to give you, so it's a single source, shortest path algorithm for unweighted graphs. So I will go over weighted graphs either today or for sure next week, but unweighted graphs mean that every edge has no weight, or they all have the same weight. So there's no biasness for every edge. Every edge is the same weight, so it's unweighted basically. So we can almost, if they all have the same weight, then we can really just not have any weights at all. So what this does is breadth first search, if you have some starting node, it finds the minimum weight or shortest path from your starting node to all nodes in your graph. And this algorithm is not recursive, which is already a victory there. The recursion is definitely not our favorite topic, so that's already a positive. So far, it's already a much better lecture already right now. The fact that it's not recursive, so we're good there. And the I guess what happens is we use a first in, first out queue is used to maintain the order of nodes. So depth first search, since it used recursion, then inherently a stack was used to maintain the order of the nodes. So when you call a function, you pushed a node onto your stack. And you returned out of a function, you popped a node off of the stack essentially. So a stack was used to maintain. You didn't have to directly use a stack, but it was automatically used because recursion inherently uses a stack to maintain function calls. So breadth first search uses a queue to maintain all of that. So basically, so that's sort of the idea. So let's go ahead and sort of write the code for breadth first, or write the code breadth first search. So pretty much the same idea. So you're going to have a starting node, and you're going to have your graph as an adjacency list, of course. You're going to have visited array. So anyway, let's go ahead and just write the function actually, and then I'll talk about it some more. So we'll have a void. I'll call it BFS for breadth first search. And we're going to have two parameters. And we're going to assume that the nodes will be labeled by integers. So this int will be the start node. So of course, it could be a different type, but so it depends on what we label our nodes. So we'll do a templated, I mean, I guess for our assignment, it'll be kind of a templated-ish type of sort of structure because we're going to use maybe a string to label a node, not an int. So then we use a hash map to map sort of a vertex name to its adjacency list. So when I cover assignment 9, we'll talk about that at that point. But anyway, for now, we'll use integers as our labels for our nodes. And of course, we're going to have our graph passed in, which will be our adjacency list. So those are going to be our two variables. Now, within our function body, we're going to create sort of our visited array. So for now, we'll just assume, I guess I could have passed it into a parameter into this function, but I guess I'm just going to just not pass it in, but we're going to have, let's put this here, visit our vertices, sorry. So we have to have a vertices counter. So, I mean, I guess we could pass this into the function or have it as a global variable. I mean, I guess for now I'm not going to really worry about that, but okay, fine, sure. Maybe I'll just add this into the function, int vertices, sure. There, so we passed in how many vertices this graph is going to have. And then, of course, we're going to allocate this visited array. I'm also going to have my predecessor arrays as well. Predecessor array. Remember, this is actually used if I wanted to construct my path, then I would actually use this array. So I'll also go over this as well because we want to construct our path potentially as well. So same idea like that for search. When every time we're going to process a new node, a new neighbor, we're going to update the predecessor array. So I'm going to leave this part out for right now, but actually, I have to do one more thing. My mistake. We have to create our queue object. So I guess I'm going to use the STL queue in C++. So it'll be just queue int, and I'll call it BFS queue. That's going to be our queue structure that's going to maintain our nodes. And then you have to go ahead and also set, so every element in visited, you're going to set them to false, of course, because initially nothing hasn't visited yet. And then every element in predecessor, maybe set them to some kind of default, maybe in this case, -1, I guess, but set them to some default sort of value that denotes that there's no predecessor. So some way, for whatever type this is, just make sure you have some default value that denotes that it has no predecessor initially. Okay, so the first thing we'll do is we're going to have our start node. So we're going to start from our start node, and we're going to try to run this breadth first search algorithm. The first thing we'll do is we're going to mark visited your start node to true. So we're going to explore this start node first. So we're going to mark it as visited. So in this case, for this breadth first search algorithm, we're going to so whenever time we mark visited true, that means that node has either been processed or we've already put it onto our queue. That's the whole idea. So which means we've already seen this node before. So we don't want to have duplicate elements on our queue anytime. And of course, we'll have our predecessor array. And I'll just for consistency, I guess, I'll just set this as -1 because this node is our starting node, so it has no predecessor, basically. And then I'm going to take my BFS queue. I believe NQ, it could be a pushback NQ, whatever you want to call it. You want to insert into this queue. So I think at least in terms of theoretical, for this theoretical version of a queue, NQ is that function that inserts an element to the back of the queue. Maybe for the actual STL queue in C++, it's push back or something, but we're going to insert to the back of the queue. That's what we're doing right there. And then we're going to have this while loop. So while not BFS queue dot empty. So basically, this is going to, this while loop will keep running as long as our queue is on empty. Now, obviously, right here, looking at this code, our queue has one element on it, at least, right? Because we just pushed the start node. So our queue is definitely not empty. So we're going to do the following. I'm going to create a variable int v will equal bfs queue. I'm not sure what the function calls are for this, but I want to first retrieve that front element. So I guess I'm going to call it front for right now. I want to get that front element of my queue. Then I want to go ahead and remove it. So I think at least theoretically it's dequeue is that function that removes an element from our queue. So I'm popping the queue. So I'm removing an element from the queue. And since it's a first in, first out queue, we're going to remove something from the front of the queue. And now we're going to iterate through all of these neighbors using a for loop, our standard for loop to traverse through all the neighbors. So I will point to that first neighbor in V's adjacency list or V's neighbors list. Then I not equal to null. And then I equals I arrow link. That's that standard method. We're going to iterate through all of V's neighbors, all the edges that V goes from to a new node. And of course, we're going to check. We're going to say, well, I'll put a bracket here. We're going to check and see, well, if not visited, I arrow. I think I use ID for this class. I use ID as sort of that field that sort of tells me. So I arrow ID is going to be the node name of a neighbor of V. So if a neighbor of V is not visited, well, then we're going to go ahead and we're going to insert this node into my queue. And we're going to later on, we're going to explore it at some point. So we're going to go ahead. I'm going to mark this as visited. I'm going to also set the predecessor array. So predecessors. Predecessor, okay, perfect. The predecessor I arrow ID equals V. So same idea with like depth first search. We're going to this new node. I arrow ID is some node ID. And to get here, we're going there from V. So from V, we're going to this new node. So that means this new node's predecessor is going to be V. And then, of course, we're going to insert this into my queue. And I guess this function also ends as well. Actually, this ends this ends the while loop. This ends the function. Zoom out so we can see the entire code. Hopefully it's still kind of visible. You can still kind of see this on WebEx, but there's the entire code. Of course, I'm going to post this PDF up onto Canvas either way, but you can see the entire thing right there. So a very simple program. I mean, there's no recursion, so it's already a victory right there. At some point, what will happen is once we explore a node, we will not be able to push any more neighbors onto our queue because either we have no neighbors or every neighbor we have has either already been processed or already put onto my queue. Now, one thing I actually forgot to put is I guess I didn't put a cout statement over here. Let me go ahead and add a cout statement to this. I'm going to go ahead and just maybe move these lines of code below a bit. It's not really important to do a cout, but I guess I'll just be consistent since depth first search had cout. I guess sure, why not? So I think I'll put it over there. So I'll just cout v and l. And once again, this could be more than just cout, but for now, I guess we'll just put it as cout. Once again, remember, we could do more things than just simply cout. We also could do other things as well after we are done with that for loop. We can also do other types of work as well, but anyway, just, there's your cout. Okay, so now I think our function DFS is now complete. Let's go ahead and sort of create an example graph and run breadth first search on this and just trace this out and try to compare and contrast this to depth first search. Okay. So I'm going to now, I'll zoom in a little bit on this. I'm going to create an example graph over here. Maybe I'll zoom out a little bit so I have more space to do this. Let's go ahead and create a graph. All right, so let me just insert some nodes here and there. Let's put this over here. Let's see, so 1, 2, 3, 4, 5, 6, 7, and 8. Okay, perfect. And let's go ahead and sort of add edges into this graph. Let's see. Oh, here we go. Let's add this edge in. Okay, I think we're good there. We add one more over here. Okay, I think that's good. So let me go ahead and just I'm gonna make this a directed graph. So I'm gonna add the directions over here. Let's see. I think I'm going to go ahead and do this maybe instead. There we go, like that. I'll put arrow over here, arrow over there as well. This, like this. I guess that works. That's a good enough example. I mean, I'm not really best at on the fly to think of a great example. I think that will work good enough. So let's go ahead and add our numbers, so our IDs to these nodes. You can zoom in a little bit on this so we can see it a little bit better there we go. So there's our graph. I'll do every single, oops, I think I'm missing one. Okay, I'm missing an arrow here. My mistake. Okay, I think now we're good. So I guess I'll make a directed graph. Okay, so let's go ahead and set up our depth first search traversal. So of course, we're going to have our visited array. So I'm going to go ahead and put that below. So I'll write this maybe in, so I'll write this below over here and put a box over here. Visited array, and we have 8 nodes, I believe, so 7 lines. This is not really even. Let's try this again. Better. I'm going to copy this. We have our 2 arrays. We're going to first have our visited array, and then of course we'll have our predecessor array. So I'm just going to try to align them a little nicer. Let's go ahead and label these. This will be visited. This will be my predecessor. And all of these will initially contain false. So we'll have a loop that's going to set every element in this array to all contain falses. And I'll use, I guess, -1s for all of these. Essentially, we have no predecessor. Nothing's really happened yet. Then we'll have our BFSQ below. So I'll put this over here below. I'll use red to be consistent. And paste this. That. Put another line over here. Like so. I think we're finally done with the setup. This will be my BFSQ. So it's going to basically, we're going to insert from left to right. Actually, I probably should have left this part out. I mistake. So here's our queue. So it's like a line. So we're going to insert elements from left to right. So our line goes from left to right, basically. So we'll do examples of this. And I'll put the output portion over here. So I think this looks okay. Okay, awesome. So we have our structures set up. Let me zoom out a little bit so we can kind of go back and forth. So basically, the first thing we'll do is our start node. I guess I'll put a green arrow here, implying that 0 will be our start node. Now, any node can be our start node. It doesn't have to be 0, but I'm going to pick 0 for my start node just because. So what we're going to first do is we're going to first mark 0 as visited. I'll put a blue dot here, implying that we've already seen this node. And we're going to mark 0's predecessor as -1. So there's that. And we're going to insert 0 into my BFSQ. Now we're going to run our program. So of course you have the code above. You can look at that. But anyway, remember how this code works. It will stop once our queue is empty. Right here, we can definitely see we have something on our queue. So we're going to have to do some work. So the first thing we do in our while loop is, of course, we pop our queue. So v is going to contain the value 0. I'll put this below, put v over here. So v is going to contain 0. That's going to be what we just recently popped off of the queue. And of course, we're going to output 0 to the screen because the code has an output. It's not really important, the output, but I guess I'll output, sure. So what we're going to do now is looking at 0. I'm going to go through every one of 0's neighbors. Okay, so 0 has, looks like 2 neighbors, 2 outgoing neighbors. So 0 goes to 2 and 0 goes to 3. So we first look at the first neighbor of 0, which is 2, and 2 is actually not visited because visited index 2 contains false. So, okay, cool, we can go ahead and explore. So we're going to mark 2 as now visited. And we're going to set 2's predecessor to be 0. Remember how the code works. We have predecessor I arrow ID equals v. So I arrow ID is going to be 2 at this moment. V is 0. So 2's predecessor will be 0. So we came from 0 to get to 2. And then we're going to insert 2 onto my BFS queue. Now my next neighbor of 0, so you first looked at 2. Our next neighbor of 0 is going to be 3. So remember that for loop iterates through all of v's neighbors. In this case, v will be 0. So our first neighbor was 2. Our next iteration of our for loop, we look at our next neighbor, which will be 3 in this case. And 3 is also not visited because visited index 3 contains false. So we're going to mark it as visited. And we're going to set 3's predecessor to be 0, which means that we came from 0 to get to this node 3. And then we're going to insert 3 onto my queue. And then we're done with that one iteration. Because let's look at our code for a second. This for loop looked at v's neighbors. So 0's neighbors looked at first I arrow ID was first 2. Then it was 3. This for loop is now done. We jump to the top of our while and we check our queue is not empty. So we have elements 2 and 3 on our queue, so we have to keep on working. So first thing we'll do is we're going to pop the queue. So we're going to basically pop 2 off of the queue, and v is now going to contain 2. And of course, we'll first output 2 to the screen. That's what the code does. And then we're going to basically look at all of 2's neighbors. So 2 has only one neighbor that goes to 6, and 6 is not marked visited. So that means we can go ahead and we can explore 6. Not right now, but we'll explore it later on. So we're going to go ahead. So visited 6 contains false. Now it's going to contain true. And we're going to mark it as visited. And then visited 6 is going to contain 2. Because we came from node 6 to get, we came from node 2 to get to node 6. So predecessor 6 contains 2. So node 6, we came from 2 to get to 6. Then we're going to push 6 onto my queue. So now we'll process 3 next, but just before we do that, we can see here the difference with breadth first search versus depth first search, because depth first search does the following. When we looked at 0, when we first looked at 2, we would go from 2 explore 6 right away. But see, right here, the queue, we're not going to explore immediately. We're first inserting an element onto the queue, which is going to just contain the nodes that we're going to explore eventually, but not right away. That first search looked at 0, then would have gone to 2, and then would have gone to 6 immediately. But here we don't do that. We first looked at 0, then looked at 2. We're going to process 3 next. But 6 is waiting to be processed. So we don't process 6 immediately. Whereas in depth first search, we just process, we go from 0, pick a neighbor, yes. 2, okay, 2, pick a neighbor, 6, yes, go to 6. Don't really think about it, just go there. But here we're actually inserting all neighbors onto our queue, and then they will be processed later on. So that's kind of the idea here. So we don't process 6 immediately, we just push it onto the queue, and we're going to process 6 later on. But anyway, that was only neighbor of 2, so that for loop is now done. We jump to the top of that while loop, and our queue is not empty, so we have to keep on working. So our next thing we're going to do is going to pop the queue again. We pop 3, and 3 is going to be assigned to V. So go ahead and we're going to output 3 to the screen. And now we're going to insert all of 3's neighbors onto our queue. So 3, let's see. So 3 has a neighbor 1, and 1 has not been visited yet. So we're going to go ahead and mark it as visited. We're also going to set 1's predecessor to be 3. So he came from 1. Sorry. So predecessor of 1 will be 3. So he came from 3 to get to node 1, because 3 is a predecessor, the neighbor. So 3 was a node that we had to get to in order to get to node 1. And then we're going to insert 1 onto my queue. Then 3 has a neighbor 6, but 6 is already marked visited, which implies either 6 has been already processed or 6 has to be on the queue. One of those two things happens. So which means we don't want to insert 6 onto my queue because we already processed 6. So the idea is this implies that we found another path to 6. But this path to 6 is either worse or not better than our already. So you already found a path to 6. So if you already found one, that means either this path right here is equally as good or it's worse. It's not a better path, actually. So there's no point to actually process or insert 6 onto the queue, because this is not going to be a better path. So anyway, we're gonna ignore this. So the other neighbor we have for 3 would be, well, it looks like 4 is a neighbor of 3 as well. And 4 is not marked visited. So we're going to go ahead and mark it as visited. And then 4's predecessor is going to be 3. So we came from 3 to get to node 4. And I'm going to insert 4 onto my queue. And now the last neighbor, actually not last 2 neighbors, so 3 has neighbor 5 and 7. So wow, looks like 3 really is like that anchor, basically, because everything goes from 3, or at least for the most part. So interesting graph. So 3 goes to 5, and 5 is not visited. So we're going to go ahead and mark it as visited. And 5's predecessor is going to be 3. And we're going to insert 5 onto the queue. And then 3's other neighbor is going to be 7. 7 is not visited, so we're going to mark it as visited. And we're going to set 7's predecessor to be 3. So at this point now we're kind of done, but I'll go through the motions either way, but we're kind of done at this point because everything has been already processed. But the idea is that the actual algorithm itself can't really know that's already done. Now, we know it's done because everything visited all contains true. So we could have a loop that could go ahead and traverse this array to see if everything is going to contain true. But if you were to actually add this to breadth first search, the runtime would get hurt, actually. So let's say in my while loop, I add a for loop that would go ahead and traverse through my visited array to check if there's any falses. That would actually increase the runtime to this breadth first search. So doing this actually is not really a better idea. So it's better off actually time-wise to go ahead and just pop the queue a few more times. It's still better than constantly every single time we insert to check this array if everything contains true. That's going to hurt the runtime actually for breadth first search. So we shouldn't really stop right here. So we'll do the rest of this. We'll go through the motions here, I suppose. So anyway, after we push all of 3's neighbors onto the queue, So I mean, so if you had another variable, so one to store number of true vertices and one to contain, I guess you could have a counter every time you actually, I guess one thing you could do every time you actually update a vertex in your listed array, increase a counter, I suppose. If that counter equals vertices, you can stop right there. So yeah, I guess you could do that. So yeah, that would actually, yeah, that would let you stop that breadth first search earlier. I guess I won't do that, but yeah, of course you could do that. It wouldn't make in the worst case, it wouldn't really make any difference. But yeah, you could probably end the loop earlier, and that would be a method for sure. But I guess we'll go ahead and just go through this either way, though, just because. So the next step is our queue is not empty. So we're going to go ahead and we're going to pop the queue again, and V will contain the node 6. The first thing to do is we'll output 6 to the screen, just like that. And for 6, only has one outgoing neighbor, 7, but 7's already been processed, so we don't push anything into our queue. All right. Then we're going to go ahead and go to the top. Our queue is not empty. We pop our queue. Look at node 1. We output 1. We check. So 1 has no new neighbors. Not 1 has neighbor 2, but 2 has been marked visited already. So the idea here is, here's an example. So we found a path from 1 to 2. However, this path is not actually better. And the proof is that because we're using this breadth first search, or using this, this FIFO queue, that means the first instance we pop an element off of the queue, that is actually the shortest path from your start node to that node. So if other paths are found later on, that cannot be a better path. So you found a path from 0 to 2 that goes through 1, but it's not better. We already found a path earlier that went from 0 to 2, which was just that one edge right there from 0 to 2. And that was the best path. So the idea is that because the way how breadth first search works, it's sort of this, when it discovers a node for the first time, that's actually the best possible path. That's the shortest path to that node. Because the way we actually process nodes level by level, the first instance we find a node, that's the best possible path. If you find another path later on, it can't be better, is the idea. That's like the proof of why breadth first search is going to work. Why it always gives us the best path. Anyway, we're going to pop the queue again. Either queue is not empty. Looking at now VOB4. We output 4 to the screen. 4 has 2 neighbors, 0 and 5, but we've already looked at 0 and 5, which means we already found a best possible path to 0 and to 5. So therefore, well, we already found a path that was equally as good to 5 that goes through 3. So there's no point doing anything here. So we're done. We pop the queue again. 5 goes into V. Output 5 or V. 5 has nowhere to go. We don't push anything onto our queue. We pop the queue again. Looking at node 7, we output 7. 7 has no neighbors, so we don't push anything to our queue. Our queue is not empty, which means that we're done. So the only really important part is this predecessor array. This is going to be how we can construct our paths. And breadth first search will give us our best possible path. So looking at this, if I want to find a path from 0 to 1, let's say. Well, what we can do is if I want to find a path, so output, or actually find path from 0 to 1, or yeah, 0 to 1. 0 to 1. The way we do this is we'll have our stack. Not a straight line, but not a very nice looking box, but good enough. We first push 1 onto our stack, and in 1's predecessor is going to be, obviously, we can see it's 3. We push 3. 3's predecessor is 0. Push 0. 0's predecessor is -1, so we're done. So our stack from top to bottom is our path. So 0 to 3 to 1. And this path is going to be the best path. So breadth first search always finds the best path from your start node to every node in your graph. So the idea here is because of the way we actually traverse. Looking at this, let me go ahead and just use a space pen for a second. So first, when we're going from 0, we're first going to expand this level. Then from 3, well, we're going to expand. So we're looking at this. Then we expand all of 3's neighbors. Next is our first level, second level. Then we have, let's see, then we have our third level, I believe. Actually, not really, because 2 is part of this. So really, we only have 2 levels, I think. 1 and then 2, and that's really it. Because after that, there's no further. I guess that's, oh well, I suppose. It's ended up being a very simple example. But the idea is we process level by level. So we first put all 0's neighbors onto our queue, and then we put all of those neighbors onto the queue next. So you first have to process all the neighbors in one level before we can process the neighbors in the next level, and so on and so forth. So we're not going to process 1 before we process 2. We're not going to process any of these. We're not going to process 4 before we process 2 because of the way this traversal works. So because of that, we always get the best possible path. So that's why if let's say I find another path, let's say from 0 to 2, I go from 0, 3, 3 to 1, 1 to 2, we're not going to update this because we already discovered 2 from 0. But depth first search actually, if we use depth first search on this graph, there's a chance that the path it actually constructs from 0 to 2 could be 0 to 3 and 1, from 0 to 3, 3 to 1, 1 to 2. It could do that. It depends on the order in which the nodes are stored in each of these nodes adjacency neighbors list. Let's say 3 is in our list before 2 for 0's neighbors list. It would process 3 first, then from 3 we go to 1, and 1 goes to 2. But for breadth first search, regardless of the order in which we have the nodes in the neighbors list stored, let's say for 0, we have 0's first neighbor is 3, then 2, doesn't matter, because we always insert 3 and 2 before we insert any later on nodes. Because of that, it will first process 3 and 2 before it can process 3 and 2's further neighbors. So because of that, it will always guarantee the best possible path, no matter what. Always will give us the best path. So this is, since 0 was my starting node, I'll put this here. So since 0 was the start node, this instance of breadth first search constructs the shortest path from 0 to all nodes in the graph. Hopefully I'm kind of consistent with this. Okay, cool. I don't want it to be too wide right there. So anyway, so this is not going to give us, so this does not construct the shortest path between any two nodes. So this is not an all pairs shortest path algorithm. It's only going to work for a start node. So since I chose 0 for my start node, it will find the shortest path from 0 to all nodes in my graph. But it will not find the shortest path necessarily from 1 to 6 or 2 to 5. It maybe, but it's not really the purpose of it. If I wanted the shortest path from 2 to 5, I'd have to run depth first search and then pick 2 as my starting node. and then it would find the shortest path from 2 to every node in my graph. So to expand on this, if I want to construct the shortest path between any two nodes, run breadth first search and for each node, for every node. Actually, hold on. I'm trying to set so it's we want to pick each node for our start node essentially. So run BFS for every node as the start node. So basically, I have to run BFS and then choose 0. And then I have to maybe have it return this predecessor array. So this would return that to me. So this is good. This predecessor array really is the construction of my path, because I can use this array to very easily, I can use this to construct any path basically. So pretty much you have to run breadth first search and pick 0 for your start node, run breadth first search again, and have 1 as your start node, and run it again as 2 as your start node, and so forth. So you have to run this v number of times. So in other words, run BFS v number of times if you want to have all pairs, basically. But it only works, so one instance of breadth first search only will find the shortest path from your start node to every node. If you want all possible pairs, you have to run breadth first search v times, and each one would pick a different start node. So of course, I could easily, just to scroll up for a second, if I wanted to pick 2 as a start node, just at the very beginning, just go ahead and push 2 onto my queue, mark 2 visited, and then mark index 2 of predecessor to -1, and then pop 2 and then expand on 2's neighbors. I could have easily done that as well. I chose 0 just because, but any node could have been chosen. I just happened to choose 0 just because. There's no reason why I chose 0. I just chose 0. So, and its predecessor array is really the really important part of breadth first search. This is going to be what will help us construct the actual shortest possible path. So let's go over runtime analysis of breadth first search, and then we can actually sort of talk a little bit about our next algorithm. So at least we're making pretty good times. Maybe the Wednesday morning of next week, which will be Thanksgiving Eve, maybe it'll be a shorter class actually, because I might have enough stuff covered by then. So we'll have a nicer, easier Wednesday morning class. I mean, it is Thanksgiving Eve after all, which it would make sense not really have a very dense class. I mean, where's my Thanksgiving spirit, right? So anyway, runtime analysis. Pretty simple to remember this one. Same idea. Each edge is looked at once. So basically, we're going to go ahead and process a neighbor for a node, look at all those edges to see if that edge leads to a new node, to an unmarked node, or leads us to a already marked node. Either way, we have to look at that edge basically. And we don't have any, all we do is we just push a node onto the queue, we update predecessor array, mark that node visited. So all that stuff is constant basically. So we run this E number of times. So the runtime is going to just be same as depth first search, it's O of V. Now, of course, once again, it could be O of E plus V. If you look this up on Wikipedia, because it assumes, well, if it's a dense graph, it's O of V. Sparse graphs sparse graph O of V, but really it doesn't really, I don't know why they have to do that because really it depends on your edge count. So E could be V squared or it could be V. So it depends solely on your edge count. Now, of course, as I was suggested earlier, you could actually end breadth first search sooner, right? If everything has already been processed or already been marked true, you can stop right there. But in the worst case, though, you won't be able to because in the worst case, after you look at the final edge in your graph, then the last node gets finally marked, visited. So that's going to help you, that approach, to end early, but the graph could so happen to be where the very last edge happens to finally reach that final node that has not been seen just yet. I mean, for example, I could have something like this. So you process 7 last, right? Okay, I could do something like this. And then you would not be able to end the loop early or end this program early because 8 would not get processed until finally 7 finally gets popped off the queue. Then finally 8 would be able to get processed. But until then, we can't stop. So in the worst case, that wouldn't work. But of course, in other cases, though, that could end the program a little early, but that's only in certain cases. But in the worst case, though, it wouldn't help. Also, in the worst case, or an average case, you wouldn't be able to end the loop that early. So maybe it would take E over 2 number of steps it will take. It will process half the edges first, and then it will finally, okay, we'll stop. So it will still be some type of function of E. So it might be E over 2 steps, and it will stop, but it will still be, asymptotically, it will still be O of V. So there we go. That's a breadth first search, so we can kind of see at the same runtime. It's just that breadth first search guarantees the shortest path. Depth first search does not. You're probably wondering why we're using breadth first search then over depth first search or vice versa. Well, if you're just doing just a very plain basic traversal of your graph, depth first search is kind of the more simpler one, I suppose. They're both simple, but that one's kind of more generic enough. It just, the fork in the road, take it, just go. So, for topological sorting of a graph, for cycle detection in a graph, depth first search is actually a much better approach than breadth first search because breadth first search can't even find cycles that easily because you're not traversing the graph. You're sort of expanding it level by level. So you can't even tell what nodes are currently in your path to be able to even find a cycle. So it's you could use the breadth first search to find a cycle in your graph. It's just not as easy actually. It wouldn't be as simple. I mean, the obvious method would be if you have your start node 0, if there's going to be an edge that goes back to your start node, then obviously cycle is found. So that's one obvious way you can use breadth first search to find a cycle. But really, its whole purpose is just to find the shortest path. That's the whole purpose of breadth first search. Any other normal, any generic graph traversal, depth first DFS is the way to go for a generic traversal. So anyway, that concludes breadth first search. Any issues or questions on this? So I guess if you have a question, it's okay because we're going to do sort of a breadth first search again, but this time it's going to be on a weighted graph. And this, what I'm going to go over today, and I'm probably going to continue this on Monday, it'll be very similar to breadth first search, but a little bit different. Let's go ahead and cover this next algorithm. This will be Dijkstra's algorithm. So this is going to be actually a shortest path, or you can say minimum weight path algorithm on a weighted graph. So weighted graph really means that every edge has some weight, basically. They're not going to all be the same. If they're all the same weight for every single edge, then it's the same thing as having an unweighted graph, basically. So you're going to have distinct weights on your graph. So every edge will have some weight, and they're not going to all be the same, essentially, is what a weighted graph really is. So this is actually really just a BFS traversal. It is a breadth first search type traversal on weighted graphs. Now it's going to be, this is actually known as a greedy algorithm. So there are different sort of paradigms or different sort of classes of algorithms. So we covered divide and conquer earlier this semester. So divide and conquer was like merge sort, quick sort, binary search. There's also other divide and conquer problems as well, which we'll learn about that more in later on, maybe in CS477. But those are the basic ones we covered in this class, at least. So a greedy algorithm is just a paradigm of algorithms. So greedy means that it does the next best move. So it's going to choose the next best move. So algorithms always picks the next best available choice. So it has choices, it picks the best one. So that's why it's greedy. So, and it's not going to think about the future, just pick the best right now. So think of think of Mr. Krabs from SpongeBob. There, he's greedy. He sold SpongeBob for 62 cents from, to the Flying Dutchman because that was the best move right now. Right now, that was the best idea. But later on, it hurt him because he lost his best fry cook. But the idea was that right now was the best move. Now, typically, for greedy algorithms, being greedy actually does sort of give you a good, favorable results. Not in every possible sort of, environment, but for typical algorithms, a greedy approach is good. But if that's the input is not known in advance, then a greedy approach might be actually bad because in the future, making your greedy move now might hurt you in the future. But since these algorithms, the whole input is known in advance, then a greedy approach is not going to be bad. And it's going to, we actually use a priority queue min heap to enable Dijkstra's algorithm. Dijkstra's algorithm to be greedy. So the priority queue is going to enable this greediness. So typically, for most greedy algorithms, typically a priority queue is going to be used because a priority queue has a very nice property. It always has the smallest element at the root and it has a very fast runtime to, if you insert or remove something from a priority queue, it very quickly finds the next smallest element. So priority queue is going to be the enabler for most greedy algorithms, or at least the common ones, I suppose. So there we go. A priority queue is an enabler. So I don't know. Probably shouldn't be studying priority queues in 302 because enabling is always bad. So now what we're going to do is we're going to basically just, let's see, we're going to use this priority queue to help process our nodes. So for BFS, we use a first and first out queue to actually store the order. But here for Dijkstra, same idea, except we're using a priority queue instead of a first and first out queue. That's like the only real difference between Dijkstra's and BFS. There's some more differences, but that's the real basic idea. So anyway, now let's go over our Dijkstra's algorithm. So let's go ahead and just, I guess, sort of do a pseudo code of Dijkstra's algorithm. So basically, we're going to have, so here's going to be our function. So I guess I'll just call this, I'll just call it Dijkstra. So there's no return type. Just this is kind of like the pseudo code for this, Dijkstra. And we're going to pass in G, which is our graph, basically. And then I guess S, which is going to be our start node. Just like with breadth first search, we want to find shortest path or minimum weight path to our nodes from our start node S. So within our function Dijkstra, we're going to basically allocate an array W and set W index I to, I guess, to infinity for I equals 0 to B minus 1. So this is going to store the weights. So the actual weight, the path weight so from our start node to node I, it's going to store the actual weight of that path from S to I. Initially, you're going to all be infinity, which means we don't have our path weight yet. We're going to update them, essentially. And then we're going to do is we're going to set W S equals to 0. And then we're going to insert S into PQ, which is short for priority queue, our min heap, if you will. And then we're going to have this while loop. So while PQ is not empty, you can kind of see there's some similarities here to breadth first search. So anyway, so now we're going to, as always, we're going to pop the priority queue. So basically, and let me see, what's the right terminology? I guess I'll go ahead and I'll just say U equals PQ dot get min. And of course, we'll just have PQ dot delete min. So we popped our priority queue. And now we're going to do the following. So for each neighbor V of U, so we're looking at node U, and then for every neighbor, so V will be just a neighbor. And we're going to basically check and see. So first we're going to see if, maybe I'll use an asterisk over here to separate this. So if B is not processed, now the best way to check for that is if W at index V is not infinity. So the best way to check for this is if, so if W at index V is not infinity, then we know that this node has not been processed yet. If it's not processed, then we're going to go ahead and we're going to relax, which is really weird. This is the actual term to use in algorithms for this. So we're going to go ahead and relax. We're going to say we're passing U, V, and PQ. Actually, I made one mistake. I had to add this line right there. My mistake. I have to take this and put it down one level. I have to add one more thing, actually. Let me just put this down over here. Perfect. We're going to write W of u equals u dot weight. So every node will have its path weight from your start node to u. So u dot weight will be that path weight from start to u. We're going to write that into this W of u. We're going to write the actual, so once we pop an element off of our heap, that is going to be the shortest or the smallest weight path from S to U. Let's go over the relax function next. I don't know why it's called relax. I mean, it's not really relaxing. It's doing actual work here. It's kind of like, I guess it's like being on break from school, like winter break. You relax, but relax really means you still have to do work, but you're not really stressed with deadlines and so forth. At least not for school deadlines. So it's relax means you're not as stressed, but you still have to work on stuff, so you're only halfway stressed, I guess. Relax. So anyway, for relax, all we're gonna do is the following. We're gonna first check and see that if, I'll put this here like this, I'll try to be consistent. Okay. So if V is not in the priority queue. Now, the priority queue, what we did so far, does not have any function I can very quickly check to see if V is in there. So you'd have to have a special type of priority queue that after every insertion and deletion, it returns some array that kind of maps what element in the priority queue heap array does that node reside in. So because you don't want to have to linear search through the priority queue to see if V is in there. If you do that, your runtime is going to get hit, basically. So you have to have some type of parallel array structure that maps each element, each node ID, to the element in the heap array, so you know exactly where it needs to be in the heap array. But we'll just sort of, for now, use magic, and we just sort of know that we can sort of tell in constant time that V is not in the priority queue. If that's the case, well then, we're going to go ahead and insert. So then I guess we'll say V's weight is going to really be just U's weight plus edge weight from U to V. Then we're going to insert V into the priority queue, which will bubble up V basically. And now if, so let's say we know for sure that V is in the priority queue. So if U dot weight plus edge weight from U to V is less than V's current weight we have right now, we found a better weight. So then we're going to go ahead and update V dot weight. We'll assign it to be just U dot weight plus edge weight UV. And then we can, of course, we're going to bubble up V in the priority queue. Now, of course, we could also if you had a predecessor array, if we have to actually relax this node, then we actually would set the predecessor of V would equal U. If let's say you found, let's say if V is not in our priority queue, if we insert V to the priority queue, we first have to set predecessor V equal to U. And for the other if statement, if you found a shorter path to V, we'd also would update the predecessor array as well, but we're not going to focus on that right now. So the whole point of relax is the following. Here's how it's going to work. Let's say we have these three nodes over here, like so. We have let's say we have, this is going to be basically X, this will be U, and this is going to be V. Hopefully this doesn't really spell anything bad. And we have sort of a path from x to v. It's going to actually contain multiple nodes. So we have some weight. So from x to v, we found some weight, basically, a path weight. Now we have x goes to u with some weight as well. Then we have this edge from u to v. So let's say we have this path weight from x to v with a certain weight, and we have a path weight from x to u. Actually, I'll use blue, I guess. And this. So let's say the path weight from x to u, that whole path weight, plus that edge from u to v is shorter than this amount, that path weight, then I found a better path weight. So I'm going to go ahead and update v's weight to be the path weight from x to u plus that edge weight from u to v. That's my new shorter path. So we're constantly relaxing nodes until you find the best possible path. So we may find a path at some point, awesome, but you may find a better path as we traverse our nodes. So relax means we're trying to find a better path, basically. But once we pop a node off of the heap, there cannot be a better, smaller path weight from starting node to that node. And we'll go over as to why, because, well, the one main restriction for Dijkstra's algorithm is that you can't have negative edges. If you did, this greedy approach actually would not work. So there's an example right there where greediness is great, but negative edges would break this greedy algorithm and it would not work correctly. But we'll worry about that more, I guess, next time. So I guess for right now, we're almost at time. So I guess we'll go ahead and stop class right here. So I guess that's it for today. I guess take care, you guys. Thanks for watching. Stay safe. Have a great weekend. And I will see you guys next week.